And what is more important is the interpretation of these two quantities. And what is SSR beta naught? Okay, so let's begin. So, what I have here is a multiple linear regression model. Response, and then there are regressor variables. And there is this intersection beta naught. Now, P is k plus 1. P is the total number of regression coefficients. K of them plus 1. So P is k plus 1. Now, I'm going to break this equation into two parts. The first part consists of beta naught, beta 1, up to beta p minus r minus 1. So, and then the rest here, plus the error term markup. So how many how many betas are there here in the first part? You can find easily, right? Is p minus r of that. And then the rest are in the second portion. So in matrix notation, I can write this. Originally it's just x beta, but I'm writing it as x1. So the x1 are the regressor values corresponding to beta 1. x2 are the regressor values corresponding to beta 2. So in matrix notation, this is what it is. You can multiply out to get the 2. Okay? x1 beta 1 and x2 beta 2 plus epsilon. So how many regression coefficients are there? P minus r. Beta 2, r of that. Alright. So let's try to understand these matrices x1 and x2 better, so that we know what we are doing. So if I write it out in full, you will know what is x1, x2, beta 1, beta 2. So beta 1 is just the first p minus r regression coefficient, and then these are the regressor values corresponding to them. And then beta 2 is the r regression coefficient and the x values corresponding to them. So you need to understand what x1, x2 means. Yeah, this notation. So these are the matrices. All right. So now, SSR beta. Okay. So here I'm going to make some definition. So maybe I should put 3 lines. So these are definitions. Actually, the definition is here. This one. So SSR beta, when I expand it, it means beta naught, beta 1 up to beta k. Now beta 1 comprises the first p minus r regression coefficient. So it's beta naught, beta 1 up to here. And beta 2 is the same. Alright? I am going to, so this, here there are three lines there. It means it's a definition. Yeah. So this means definition. Okay? So if you see 3 lines, it means I define this. So I define this, beta transpose times x transpose y is this. And so on. For beta 1 transpose, x1 transpose, and y. So that's step 1. Can everybody follow? Alright, next is another important definition. This definition says that, okay, how do I read this? This is sum of square of regression, or sum of square due to the regression model of beta 2 given beta 1 already in the model. So this is the sum of square of regression due to beta 2 given that beta 1 is already in the model. So that's what it means. So what does that mean? Already in the model. I will explain that very shortly. So this quantity is defined to be this. So far we have not used any condition. Yeah? So I define this to be the difference between these two. Okay? So that's what it is. So in our case, beta 2 is the R, beta 2 is just P, beta P minus R to beta K. And then beta 1 is the first P minus R regression coefficient. So given this. And then this is defined, defined to be this. So I'm writing out this equation in full for you to see what is inside there. So these two equations, of course, are the same. I'm just writing out all the betas for you to see. Beta 1 and beta 2 together is beta naught to beta k. And then beta 1 is just the first P minus R regression coefficient. Can you follow? Okay? Now, so how do we interpret this? This quantity. So how do we interpret this? This is an important idea. A very important idea in multiple linear regression. Well, let's look at it. So this is my note here. My notes here for interpretation. Well, we know this. This one, we already know. What is SSR beta? It denotes the regression sum of squares due to beta. So as I've explained at the beginning of today's lecture, if the regressor associated with this beta, let's say highly related to the response, then this SSR beta will be large. If the response y does not depend on the regressor variables, then this sum of square, the regression sum of square due to beta will be small. If this is small, then the sum of square residue will be large. Okay, sum of square residue large means, hey, your y doesn't depend on the regressor so much. Now what about this? what is SSR beta 2 given beta 1? So this is what I want you to know today. This is called the regression sum of squares due to beta 2, given that beta 1 is already in the model. Okay? So I still have not explained to you what does it mean to be already in the model. Yeah? So you need to understand this. Alright? Because it's very important. So let's look at one example called a two-life data that we will come to later in this course. In this experiment, we want to know how is the lifetime of a tool depends on tool speed and the tool type. This is a tool. This is, now this will turn. And then you put the tool here, you can, you can make this smaller. You can somehow reduce the diameter or whatever. So that's the idea. So you have a tool here, and then this will turn at certain speed. So there's this speed here. Of course, the faster you turn, there will be more friction between these two, right? And so the life will get shorter. Is that right? So one thing we know for sure, if I increase the speed, no matter what type of tool I use, the lifetime of the tool will get shorter. Is that true? And of course, the lifetime of this tool depends not just on the speed, but it also depends on what kind of material you use here. If you use, let's say, a type of steel that is hardened, then it will last longer. If you use a pig iron, hey, within seconds it's gone. You know? If this is weaker than this, I tell you, this will go immediately. So the lifetime of a tool depends on the speed at which it works and the type of tool. And let's say in this experiment we have two tool types, A and B. You know, you could examine one made in, let's say, Singapore, one made in China. You know, compare them. Yeah? See how well it works. I don't know which one will work better. China is very powerful now. So we don't know. So we can do a test. And then for each type, you can vary the speed. Here also you vary the speed. And then you collect the two lines. You just perform the experiment until the tool is gone, finished. So there's some definition for a lifetime. Say it doesn't work anymore. That's the life. So I want to show you the data for this, the data set, a graph for this data set. So here is the lifetime of the tool. And here's the speed at which you operate. Tool type A denoted by red square. Tool type B denoted by blue square. Okay? So, this is of course tool type of course is called X2. Well, what do I? So we are interested in the lifetime of the two. All right, these two types, we're going to compare so that whichever lasts longer, we'll buy it. So in a way, we want to test this. We want to test beta 2 given beta naught. This is called SSR using our usual notation that is called SSR. Alright? Beta 2 given beta naught. Let me just check one more time. Okay, so that's fine. And so what will happen? So here, if you look at this, what I've written there, it says we are going to test the two types. Did you see two speed in that expression? Beta 1 is not in that expression, right? That means when I use this to do my test, I have not considered two speed at all. So when I do not consider two speed in my test, that means I'm only looking at x2. For two type A, I calculate the average lifetime, right? And then for two type B, I calculate the average lifetime. And then I compare these two lifetime. And when in this comparison, I don't take two speed into consideration. So let's say the mean of two type A is somewhere here. You take the average of all the red squares, you will get a big one here. That's the mean. So this is the mean of all these here, all these points here, this value. So it's about, 18. What about the mean of the lifetime of two type B? Well, you'll be somewhere, let's say here. Yeah? So, is there any difference between these two? Well, big difference. So when you test it, you will find that, yes, two type B is in fact better than two type A in terms of lifetime. So no ambiguity here. You understand that? So here I have never considered this. I've never considered this in my test here. Now let me show you another situation. Suppose, so this is the actual experiment done. Suppose I perform the experiment this way. Let's say I wasn't too careful. I collected more here. I wasn't careful, so for type A, I collected a lot more here at low speed. Okay? And at the same time, for the two type B, I collected many here. I did it for a high speed. So that's my data now. Here's my data. For low speed, two type A, I test a lot of them at low speed. Two type B, I test a lot of them at high speed. Well, I'm still going to I'm still going to test SSR beta 2 given beta naught. Given beta naught means we are not testing beta naught, we just want to test beta 2. You fit a regression model. Y equal to beta naught plus beta 2 x2 plus epsilon. That's what it is. And when you test whether beta 2 is 0 or not, that's what you are testing. Okay? That's what it is. Is there any x1 in the equation? None. Okay? None. So what happened now is you have you calculated the mean of all this. So maybe it's here now, because you have a lot of points here. And for the other one, for 2 type A, you calculated it. It could be even higher. You know, it could be even higher, or in this case, in fact, they look like the same. Because of the way I collected my data, I wasn't careful enough. Now the two means are very similar. So when I test this, when I test the difference between the two types, so testing beta 2 equal to 0 amounts to testing the difference between the two types. But because of the way I collected my data, you can see that there's no difference. The test will not be significant. Even though we know 2 type A has a shorter lifetime than 2 type B. But because of the way I collected the data, the test shows that there's no difference between these two types. Yeah? So what's the problem? The problem is that we did not take this into consideration. If you take this into consideration, you would have to compare, you know, for example, at this low speed, you compare the mean here with the mean here. At moderate speed, you compare the mean here with the mean here. And then at high speed, you compare the mean here and the mean here. And then you find that there will be big difference. The difference here is big. The difference here is big. In fact, it's always big. 2 type B always outperform 2 type A for all speed. And that is the truth. So, this is not going to work if you are doing this test. Why? Because 2 speed is a very important factor affecting the lifetime. And you have not considered it. So, if you miss out an important regressor, you could get nonsensical result. If I collect even more, I can even show that the mean of this is higher than this. The other one, it can give you totally surprising result. So what we want to do is to fit this model. Fit this model and test this. We want to test using sum of square regression due to beta 2 after we have taken speed into consideration. So taking speed into consideration means you are going to examine now the difference between the two means for a fixed xi. And then you vary across and then look at the average difference. And this is what is measured by this. So that's what it means by accounting for the speed. Okay? Surely we have to account for the speed. when we compare the lifetime of these two types. If you don't account for it, in other words, if you don't take two speed into consideration, your result is actually quite useless. Yeah? Can in fact be misleading. So that's what I trying to explain here. Okay? So in a way, this quantity this quantity is measuring. You know, what is it measuring? This quantity is measuring, you know, what is the increase in the sum of square of regression due to the two types after we have accounted for two speed. Yeah, that's what it is. That means, what it means is this. So let me write this down. So that's our definition, right? SSR beta 2, given these two, is the difference between these two. Now, these two are easy to understand. Now, what is this? This is the sum of square of regression when you fit a model with two speed alone. Alright? This is the sum of square of regression, or the regression sum of square, when you fit a model with speed and the two time. That means, when I fit this model, I will get certain sum of square, yeah, some value. Let's say 100. Let's make it easy for comparison. Let's say the sum of square of regression due to speed alone is approximately 100. And here, let me see. Now here, I include a new regressor 2 times. And then I calculate the regression sum of square. Has it changed a lot? If I include this, and this quantity, let's say it's 101, so there's very little change, 1%. So I know this is pretty much useless. But if I include this, and it causes a big change in the sum of square regression, from 100 to, let's say, 250, so this is 250, this is 100. So I know two type must be significant in affecting the two line. After I have taken two speed into consideration. That's what it means. Okay? I hope you understand that. All right. So what's next? What's next is we need to understand what is SSR beta. SSR beta naught is obtained by fitting this model, epsilon. And you can work it out to be n y bar squared. So let's consider this model without any regressors. So I equal to beta naught plus epsilon I, and in matrix notation is this. So y is the vector of y. The X matrix now is a vector of 1. It's just y equal to beta. So it's 1 plus epsilon n. And how do you find beta naught? So there's one regression coefficient. And we can what? We can minimize the least square function easily. And it's the same formula, you know, x prime x inverse x prime y. So this is the regression coefficient. And it turned out to be y bar. Is that surprising? Beta naught actually is an estimate of the overall mean of y. Yeah, so it's not surprising. So what is SSR beta naught? SSR beta naught, according to what we know, is beta transpose, right? But this is a scalar, I don't need to put a transpose. X transpose y. X is vector of 1. Vector of 1 times vector of y is just the sum. And beta naught is y bar. So this is n y bar. So together, n y bar squared. So SSR beta naught denotes the regression sum of squared due to beta naught. You know, just like the usual definition. But SSR beta naught plays an important part. Maybe not very important, but without SSR, without a good understanding of SSR beta naught, you will have a lot of trouble. So, when I fit this model, in fact, I am trying to test whether beta naught is equal to 0. Alright? So in a way, I am trying to test whether this random sample, y1 to yn, does the data set come from a normal population with mean 0? So, well, if you have a sample taken from a normal population, you learn how to do tests in this course here called ST3131 Introduction to Statistics. You use a t-test. You use the overall, the sample mean minus 0 divided by the standard deviation divided by square root of n. And this is a t-statistics with n minus 1 degrees of freedom. So here's the sample standard deviation. That's what you learn in ST3131. So this is not new. I assume you know it. So that's number 1. That's 1. Now, 2 is, how about, can we do the test according to the decomposition of variance or not? Yeah? Hey, by the way, we've been using decomposition. I was talking about decomposition of variance to test the overall model, right? Can we use the same idea to test beta naught, whether it is equal to 0 or not? And the answer is definitely yes. So y prime y, it's sum of square residue plus beta naught at x prime y. You can put a transpose if you want, if it makes you feel comfortable. But the transpose of a scalar is a scalar. It makes no difference. So here, this quantity is defined to be SSR beta naught. That's a definition. All right. So what is SSR beta naught? ny bar squared. So how do we do test? This is your experimental error, estimate of your experimental error. So we test this, the variation here, with this. The same idea as before, nothing new. So what's the degree of freedom for this sum of squares? 1, because there's only one parameter to be tested. What is the degree of freedom for the residue? N minus 1. This is n. This is 1. This is n minus 1 because there's one constraint involved in estimating beta naught. So the F test will be, this is a chi-square random variable, this is chi-square. So if you take the ratio, it becomes an F. And this F is this. So you reject if your F is too large, larger than the alpha percentile. Yeah? Or the one on the right hand side. And let's simplify this. Let's simplify this. F. So F is SSR beta naught over 1 divided by N. Numerator, for the numerator is ny bar squared. That's SSR beta naught. What's sum of square residue? Sum of square residue, is y prime y minus this divided by n minus 1. Exactly the way you calculated it like before. So, and then what happened here is the denominator can be simplified to this. Okay? That is your sample variance. And then you can now write it in this form. Y bar minus 0 over this. And this is t squared. Yeah. So this is a proof. This is a proof that the F statistics is actually square of the t statistics. And for this simple case, of course, and both are for testing one. Both are for testing whether beta naught is 0. That's what both are testing. So the F-test is equivalent to the t-test for testing this. And in R, if you want to fit a model, with beta only, that's what you do. Ln y tilde 1. And then if you say summary, Ln y tilde 1, or you can say t test 1, you'll be able to test this. Test for beta naught equal to 0. Okay, I guess it's quiz time. Let me turn on the quiz first, and then we will do the test. Five minutes for the quiz. After the, okay, 10:50 to 10:55 is the,
You know what? I don't understand.
and then after that we take 5 minutes break. So I will start my lecture at 11 o'clock. Alright. It's very the quiz as usual.
We learned today.
Let's just wait until 10:50. Yeah.
Chi-square, right? When I used that 0.025, it just becomes a 0.975.
Oh, good.
Is this. So the length of 5 is this. So when I do the method, right, 0.75 is the length of 5 values. 2i.
Okay. Which for me is this is all the fuck? The fuck? Wait, what? The fuck, man? You know what? It's easy. I feel like it's easy. Yes, because SSR is just explaining the rotation line and then you have to intercept. It's just an intercept. The SSR of the intercept is to intercept against the beam now. No, wait, so it's intercept line. Right?
That's so.
Choose something, then 1 minute to serve, 30 seconds to serve. So,
Four. Because only 10.
5 put it on you can also submit. I think, for sure.
So this quantity denotes the contribution of beta 2 to the sum of square of regression after we have accounted for beta 1. That's what it is. So using the two live data we know that we can't just compare the two types without taking the speed into consideration, because it might yield misleading answer. So if you take the two speed into consideration and then you test it, you'll be fine. Why is it that we cannot skip two speed? Because two speed is a very important factor, just like two type in affecting the life. And then what is SSR beta naught? When I say SSR beta naught, no matter what type of multiple linear regression model I show you, when I say this, it means this. It means you put this model and you calculate the sum of square regression due to beta naught. And it's always ny bar square, no matter what model you consider. Yeah? So, next is, what is important is this one. So we have learned SSR all along, and now we are looking at SSR beta. And now SSR beta is the more important motivation that we need to pay attention to. So now I'm going to cholesterol beta example to illustrate this idea of testing beta naught. So let's go there. So here is the cholesterol patient data. Remember, cholesterol level increases with the age of a person. And here, when I put a model without taking age into consideration, that means I'm just fitting y equal to beta naught plus alpha naught. What am I doing? Well, I am trying to test whether beta naught is 0 or not. In other words, whether the mean of the y value is close to 0 or not. That's what I'm testing. So I can do that using the composition of variance approach here, using summary and ANOVA. In fact, summary will give me the test, this will give me the evidence. Now here is to do it using inverse principle. I calculate the mean, calculate the variance standard deviation, and then find the p. And then, or you can just say p-test. Yeah, these are the functions are so rich. Just search. What do you want to do? Just search the internet. They will tell you. All right. So, so here's the t-test. I fitted the model. It tells me, it doesn't give me the ANOVA table now, because for the ANOVA analysis of variance table, it should give the corrected total variance. And so sum of square regression due to beta naught. Usually we will subtract ny bar square and it will be 0. That's why you cannot see it. But it will give you the t-test, p statistics, and the p-value. So you can see that the p statistics has a very small p-value. So it's highly significant. That means there's strong evidence that the mean cholesterol level is different from 0. As you know, it's different from 0. Yeah. We can use this t-test. It's the same. It will give you the t statistics and the t value. Look at this graph. We are trying to test whether the mean cholesterol level is different from 0. There's no need to test, right? We know it's different from 0. That's why the p-value is very, very small. Yeah? Less than some small number. Okay. So now, next, what is the difference between these two? So, in multiple linear regression, you need to understand two important notation. One is SSR beta 2 given beta 1. And another one is to understand the difference between SSR and SSR beta. I think the book did not explain it in a very friendly manner. I read it years ago, and that's why I decided to write this note for you to help you to understand the textbook. So when you go back, read the book. So, the first line is the decomposition of the variable. And then I subtract ny bar squared on both sides. Why do I subtract ny bar squared? Last time I told you I wanted to get this, right? SST. Actually, that's not the reason why we need to subtract ny bar squared. I lie. Okay? What's the true reason that we need to subtract ny bar squared? The true reason is we want SSR. Now, what is SSR? Do I care whether it's corrected sum of square or uncorrected sum of square? This uncorrected, this corrected. Do I care? I don't care. But what I care is this. SSR. Now, what is SSR? SSR, as you can see, it's beta transpose x transpose y minus n y bar squared. Now I can finally tell you the truth. No more lie. Okay? Sometimes I lie for a good reason, so that you can understand the idea better. ny bar squared is what? SSR beta naught. Okay? Now, why do I need to subtract away SSR beta naught? The reason is SSR is actually SSR beta 1 up to beta k, given that you've accounted for beta naught. In other words, SSR is to test the contribution of beta 1, beta 2, beta 3 up to beta k. That's all. Now, if you use SSR beta to do tests, what are you testing? You are testing whether beta naught is 0 or not, beta 1 is 0 or not, all the way up to k. But as I have told you, beta naught is the y-intercept. In general, this is not going to be 0. So if you do such a test with this quantity, or just this, you are almost always going to reject it. You will almost always reject the null hypothesis. So the reason, so we really got to get rid of this by subtracting SSR beta naught from it, and then test this. So this test, this SSR is this. So it allows you to test for the contribution of beta 1, beta 2, up to beta k. You got that? So SSR, so to summarize, SSR is a regression due to beta 1 up to beta k, given the beta naught is already in the model. Therefore, we use SSR to test this. 1 up to k. And if you want to test this, I don't know why. If you don't understand multiple linear regression, you might want to test this. If you understand multiple linear regression, you test it. So here, you will use this one. Okay? So, SSR is really the one that we want. Yeah? You need to account for beta naught. Here is to, we talk about the theory, but it's useless unless you know how to analyze the data using a software. In our case, the preferred software is R. You can use any other software. But in my exam, I only ask questions about R. So it's your choice. Yeah? I can use SAS, I can use statistical, Minitab, I know many. But I still find R the best. Because why? It's free. Minitab, you got to pay $1,000 if you want to install the software on your machine. So our function Lm can be used to fit this model. So when you fit this model, you need to include this, okay? Fantastic. So you can use the extracted ANOVA to get the ANOVA table, analysis of variance table. And then this ANOVA, for this statement, will produce table 1. Let's look at table 1. You see exactly what it is. So, if you do that, you will see x1, x2, x3, residue, and the corrected total here. 1 degree of freedom for each of the regression coefficient. And the first one is sum of square of regression for beta 1 after you have accounted for beta 0. Now the second one is sum of square of regression for beta 2 after you accounted for these two. The third one is beta 3 after you accounted for the other two regressive variables. So, if I want to do a test of x3, is this term significant after I accounted for these two? Then I will use this test line. What if I want to test x2 after I accounted for x1 and x3? Can I use this? Let me repeat my question. I want to test the contribution of x2 after I have accounted for x1 and x3. Can I use this second one to test? Of course not. The one that is displayed in the ANOVA table only accounted for 1. That's how they do things. Okay? So, how do you test? How do you get SSR beta 2 given beta naught, beta 1, and beta 3? You understand what I'm saying? You understand what I want? So how do you get that? How do you get SSR beta 2 given beta naught, beta 1, and beta 3? I want this. I want to test the contribution of x2 after I've accounted for 1 and 3. So how do I do that? There's a very simple way. I will just change my model to this. If I change my model to x1 plus x3 plus x2, then it will be x1, x3, x2. And then I can get the sum of square of regression that I want. Of course, you can also compare two models like what I discussed earlier. Yeah? So, remember this. And what happened here is, this is SSR beta naught, beta 1 minus SSR beta naught. And this is SSR beta naught, beta 1, beta 2 minus SSR beta naught, beta 1. Okay, just one more. This is SSR beta naught, beta 1, beta 2, beta 3 minus SSR 0, 1, 2. Do you see that? That's the meaning of it. So what do you get if you add up all this? What do you get if you add up all this? This will go. This will go. So you're left with. SSR beta naught, beta 1, beta 2, beta 3 minus SSR beta naught. So, or you will get SSR beta 1, beta 2, beta 3 even beta naught. So this is called SSR. So if you add them up, you get SSR for testing the three parameters. Alright? So that's what it is. So I mentioned to you, if you want to test beta 2 after you have accounted for x1 and x3, you can change the order, right? Well, another way to do it is to use the t-test. If you look at the t-test, table 2, you will find that it is actually based on testing beta 2 after you have accounted for all the rest. So it doesn't follow the order of the analysis of variance table. Alright? That's what it is. So let's look at an example. Don't worry if you have not been able to copy this. You can work it out yourself. It's very nicely, can be done nicely. So, look at this data set. Here I'm interested in predicting the systolic blood pressure of a person. And these are all the regressive variables. So here's the data. And I'm just going to use the first three for my illustration. I hope by now you understand that if you skip one important regress, for example, the true speed, the result that you can get can be nonsensical. Okay? So it is very important to include every important regressive variable in your model. How are we going to do that? Chapter 10. Alright, so you got to wait for a little while. But here, for illustration, I'm just going to use the first three regressive variables. So here, for example, I want to to the model. And then, as I've told you, comparing this model with beta not only, and this amounts to testing. So this will give us the sum of square of regression for beta 1, beta 2, beta 3, given beta 0. So the first part, this is the part here, and this part is here. So that's how things work. So for this particular case, I'm going to test whether the three variables, does it cause any, or does the response depend on the tree? So let's take a look. So here's my, so here I'm looking at the t-test. Because t-test here says I'm going to check the contribution of x1 after I've accounted for these two. So every one that you see here is you have accounted for the other two. That's what the t-test is. But for ANOVA, it's slightly different. Yeah. So here you can see that they are all highly significant. Yeah. Except the intercept. See, intercept usually is there's no difference. In fact, here intercept, well, there's no evidence that it is different from 0. Right? And if you look at the analysis of variance table, so to test the contribution of, x3 after you've accounted for the other two, the p-value will be this, and it will be exactly the same as this. Now, here it's testing the contribution of x2 after you have accounted for the other two is 0.00115. But if you compare with this, they are not the same. I hope you know why. Because for the analysis of variance table, here we only account for x1. This one we account for, so here is calculated based on beta 2 after you have accounted for 1 and 3. This one is beta 2 after you have accounted for 1 only. That's why these two are not the same. That's why the p-value is different for both. Okay? And now let's take a look. I think it's the same. Yeah. Here is I can compare the overall model by using this technique here, by specifying the two. And in fact, so this is the test for testing. Beta 1 equal to beta 2 equal to beta 3 equal to 0. This is the overall test. All right? And I think that's it. No? That's what it is. So, I think I'm done. Yes. So, today, we've learned this. So this is, let me just tell you what is important. This is important. And what is important is this. This is ny bar squared. Always true, no matter what model you fit. Because when you say S
Why is
bar
like
beta naught,
this?
you are just fitting this. Yeah?
Go into it.
And what's the difference between these?
What's this?
So SSR is SSR vector minus. So this is a vector. Let's just write up to. This is SSR beta naught, beta 1, all the way up to beta K minus SSR beta naught. Okay? And this quantity is SSR beta. So the difference between SSR and SSR beta is this one, which is ny bar squared. Alright? So make sure you are comfortable with the notation, because we are going to use this all the time from now on. Okay? So let me stop here now.